Yeah, what's wrong? What's the meaning? Go back to class, right?
Chinese.
Chinese, go back means die? Uh-huh.
Yeah.
What's the meaning of the go back?
Let's go back in Chinese.
Go back.
Go back.
Go back.
回来，回来。去哪里？
I like.
未来。
未来 in the future.
The future.
未来 in the
Like,
future.
I'll come back. Now go back.
Go back. 会去。
Right, yeah, not which meaning, okay. Sometimes I also expect wrong because according to my speak habit, so I just see it out, but sometimes may not right. So if if I speak wrong, that matter just give me some let me know. Yeah, let me know. Okay, doesn't matter. Okay. Come back, right? Come back to class. Yeah. What I mean is just to let you to focus, and we will begin our class. So I say come back, right? It's right? Come back. Do not you go back, right? Okay, good. Let's come back to the class. Okay. Yeah. So the permanent action I explained, they had they multiply the value because the value had this correct. So the m we calculate the permanent load will have this correct. So here scientists they measure, they do some survey or they do some research. They find for the permanent load like the gravity, they fulfill the normal, right? Normal distribution, okay? More distributions, figures, normal distribution. And the variable action, okay, here, variable action, yeah, they fulfill the different distribution here. One is the normal distribution. Normal distribution also named the nature distribution. If you learn the another class named statistic, you will systematically to learn these things. Here, yeah, in my class, I just to let you know, they fulfill the normal distribution. For the normal distribution, they had some features. They symmetry, right? Yes, symmetry. Yeah, symmetry. And for this distribution, they do not symmetry. Yeah, okay, let's see this feature. This is the normal distribution of figures. The shape will look like this, okay? Yeah, the density function can use this formula to describe this function. We use this function to draw the line, and because how we know the permanent load, they fulfill this normal distribution actually, right? Because it comes from the statistic analysis, right? Because people do lots of these samples, okay? Do lots of these samples. Some, okay, they measured how the bubbles occurs in there. They has a one value, right? Mass 1 and the mass 2. They do maybe 100 times. They found near this range, like 1 to 1.5. In this age, we do 100 samples in the experiment. We can weigh the mass, right? Get the values from the machine, right? We found there's maybe 10 samples. So the probability P is 10 divided 100. We can get a value, right? Then we use this as a horizontal, and this one as the vertical, like get some point, because they have the map. They have different groups, right? Groups, they have different values corresponding. So here. Yeah. This data support us to draw the lines, to draw the curve. Yet we find it fits the normal distribution here. So we draw the conclusion. The permanent load always fulfill the normal distribution here. But here in my class, I just give you the conclusion. You just need to know, oh, the permanent action, they fulfill the normal distribution. It's okay. And for variable action, they, according to the same process, they fulfill the distribution. And here's why we proposed these two different distributions, because the character value, this character value, we need to know, we get from the normal distribution, the curve. Like the mean value we know. In this field, mean value is the middle values, and here the peak. The meaning of the mean value is we do the statistic, the average value of the group. The average value, like average the mass, so we can the average gravity, right? Yeah, this is a character value can describe the distributions. If we know these character values, we can, according to this function, can draw the line, draw the curve, right? We will know how the character of the total things. Yeah, okay. And what another character value is a deviation, yeah, standard deviation, sigma. Right? For the distributions, the important thing is this is the average. We use the mu. This is the mean value. And also the sigma. Sigma is a standard deviation. Yeah. Okay. Yeah. The presentation value, the sigma. And here, because we want a value they can contain, right? The almost of the things, because here we mentioned the probability, right? Their probability, like why we choose at here as the value, because at here these values they can contain 95%. 95% the whole value what we measured. Yeah? Because I mentioned here, for the actual value, they sometimes have deviation, right? Deviation. This deviation, we do the statistic analysis, and we found the action, actually they fulfill a distribution. These values will near in the distribution, the curve, but we find a probability that 95%, yeah, 95%. This corresponding to the value, maybe this is a 10.7, right? This 10.7. These values at here, they can contain 95% probability of the actual value it is. Yeah. So these things in the structure design, they may contain almost a lot of possibility. Yeah, possibility. There the 5% we may do not contain. Yeah, at here, but it be accept these values contain 95%. Only 5% we do not consider these values in the structure design here. Yeah, and how to get the 95%? How to get 95% the values we fulfill this formula? This is the standard deviation. This is the mean deviation. This one plus 1.645, and then these values as a representative values during the design. Okay. Yeah, these things we know from the statistic analysis. Yeah, this is the normal distribution. Yeah, and look at this picture I get from the code. Yeah, in the future you do the structure design, you need to read the code, and you will find the table, the code they give you the tables about the different material, right? Different material, and look at here the density he lists in here. He do not give you the actual values, the density. They just give you a range, right? A range. Yeah. So how to choose the value in your design process? That we need to know, because the range means because we construct, if we use this method, because it's affected by the temperature, climate, and people's construction method. These things, all things will affect. So here, he just gives you suggest a range values that you do the calculation, do the hand calculation. Yeah. For materials, the aluminum, bronze, copper, iron, steel. Okay, they just give you the range because a lot of things will finally affect these things for density, right? For density. This is the Combi distribution. They also have the same, have different formula, but the meaning is the same, like the normal distribution. Normal distribution. Yeah, look at here for the imposed load. Imposed load, here we need to classify different the categories A, B, C, D. Yeah, A, B, C. That means later we'll choose the different value. But look at here. For the load, we choose from the code. They just give you the range. They do not give you the actual value. You need according to the actual situation to choose a value in this range in your design process. Okay? This range, I explain why the values listed in the code, they just arrange, do not give you the actual value because the values, the load, they fulfill a distribution. They have discrete. They had occasionally, they do not be concrete value, right? Concrete 具体的一个数值，具体的是仅仅OK， this thing 是具体的，具体的 ，it's just a range, right? A range values let you to choose. This for imposed load for Gangu distribution, the same like the density of the material. Yeah. Here's we know some statistic analysis about the permanent load. They fulfill the normal distribution, and for variable action or just imposed action, they fulfill the Gangu distribution. Yeah, and I just captured some table from the code. As you know, in the code, the load value chosen, they just arrange, do not give you the concrete, right? Just the same word like concrete, 具体的。张克力 do you find that?
Well, I can see what you're writing there. The handwriting is
具体的。
Wait.
Yeah.
Handwriting.
not handwriting. The character.
Character. 体
Oh, from Shanti.
身体 yeah. But here in the 具体
Right.
具体的 I know the word, the English word is same like concrete. Yeah, but they had a different meaning. 具体的 as a describable word to 具体的 value, or concrete value. Yeah, but it's specific. Yeah, specific, right? Or the same meaning of the specific. Yeah, specific value, but it just a range. Look at here. Yeah, they give you a range. So later, if you do the structure design, the values you may choose the larger, right? Larger means the load you consider is higher, and actually the load will not reach this value. Means the structure you design is more safety, right? Safety. We can simply to realize that. Yeah. Need I to explain to say it again? Yeah. Okay, I will say. Yeah, because the code, the Europe code or the Chinese code, they will list a table, a suggestion value range for you. to do the structure design, right? Just like this table, right? For QK, we choose this range, right? This range. Behind why it gives you this range, because I introduced that we use the limit state design. Limit state design, it brings the possibility in the value to make sure which value we used. Yeah. So actually, for the load, they fulfill a distribution, like a normal distribution or organic distribution. Yeah. And we use the values. They contain 95% possibility. Yeah. And for here, for this range, if we choose the larger load in your design, that means you consider the more the load, the larger the load. Actually, in reality, the load may not reach this specific value. So that means your structure, your building is more safety, right? Yeah, more safety. Okay, now we talk of another load, the wind load. They do not fulfill wind load or seismic load. The accident load, right? Accident load, they happened in short time, or maybe they have the magnitude values. Yeah, the things is different. Okay, here's I look at here. It will related to the tall buildings that we talked in the chapter 1, how tall building to take.
Wind is one of the most important factors that architects and engineers must consider when designing tall buildings. While skyscrapers might appear to be highly
how the engineer to realize the wind load, how they use some method, the solution during his high building design. They use some method
strengthened immovable structures,
to reduce
all
the
tall
wind
buildings are in fact designed with a degree of flexibility in mind. This is principally due to the impact that wind forces, known as wind loads, have on a building as it becomes taller. Whilst you
Here, I introduce a character of wind load. Wind load near the ground, the value is small. With increased altitude, right? At here in the really top, in high, in the high, the wind speed will be larger. That means the wind load, they have this pattern. Right? The load, because in the future, yeah, in the next class, you will know the wind load is related to the wind velocity. If the high wind velocity, it means high wind load. So according to this video now, we know the wind speed is higher at
might be experiencing a pleasant breeze at street level, the force of the wind generally grows much stronger the higher up you travel. While the steel and concrete used in a skyscraper's superstructure is designed to bend and flex to absorb the impact that these wind loads have, the degree to which a structure is able to move can have a significant impact on the comfort of those inside the building. When buildings first began to grow tall in the 1890s and 1900s, height limits were imposed, such as those introduced in Chicago, to prevent their masses from blocking sunlight. In New York City, ordinances were passed that allowed tall buildings to develop on the basis that they were set back after reaching a certain height. This allowed sunlight to reach street level, whilst breaking up the facade and reducing the impact that high winds had on these early towers. By the 1960s, however, larger box-like skyscrapers began to come to prevalence, bringing with them a whole host of wind-load engineering challenges. The first problem that began...
Yeah, here, I think you realize why people build high building, because in New York, right, they build a lot of high building skyscraper because of the prevent sunlight. So one building prevent sunlight, so another building you build more higher for sunlight, right? So the height of the building be higher. That occur the high building, the skyscraper that have they comes. So this is the background of the why of the high buildings occurs in our life, because they just for sunlight, like a plant, right? If the plant be higher, they can accept full the sunlight. Yeah. So that's the background.
And to arise was increased wind velocity at street level. This was principally caused by the street canyon phenomenon, an effect that sees large buildings redirect wind down their facades, which effectively act like canyon walls, and funnel it along streets at much higher velocities than in low-rise suburban areas.
Yeah, here they talk about a phenomenon, the canyon street, the street canyon. I will explain, because the background that people's, in order to build high buildings, yeah, they faced a lot of challenge. One thing is you will see in the city, right? In the city, if the high building built like here, in the middle part in there, the wind load, the wind speed, you will feel really high. This is a phenomenon called the canyon street phenomenon. I'm not sure, did you see in the river, right? In the river, this is the bridge for the pier to support the bridge, the pier. This is the river. You will see when the water comes in here, the water's velocity is really fast. This is just a phenomenon that, yeah, I think you learned the fluid mechanics. Yeah, fluid mechanics. Teacher by to talk to you. Yeah, something is related. But it's okay.
The street canyon effect was particularly notable in Manhattan, where the heavily formalized grid structure of the city blocks offered little to break up and deflect winds once they began to blow. Additionally, as wind moved around the top of these tall structures, vortices were being created in a process.
Yeah, another phenomenon of the vortices for like this is buildings, right? Wind comes behind this building, they will occur the vortices. There's two phenomena that you need to know. One is a canyon street phenomenon, and one is the vortices. Yeah. How to say? This is the building, right? Building. And if you stand at here, you will feel cool. The low temperature cool because the wind is really strong near here. This phenomenon, if you only one building you stand here, you can't feel the wind. You can't feel wind strong. But only there's two high buildings, right? Two high buildings. If you stand everywhere, if you can stand at here, it's also okay. You can feel really strong wind comes. Oh, really cool, like that. But if there's only one building, you stand here, you can't feel the phenomenon like here. This is for construct high building. There's a phenomenon that occur in the Manhattan. Because in Manhattan, these cities, there are lots of tall buildings, and like people, they're the top. So the wind in this place, right, really strong. Okay. And another phenomenon is the vortices. Vortices occurs.
It's known as vortex shedding. This process, much like water flowing downstream, acts differently on obstacles depending on how streamlined they are. In the case of these buildings, their shear block walls created a bluff obstacle that wind had to flow around. As strong winds moved around these structures, areas of low pressure emerged on the opposite side of them, creating suction forces that pulled at the buildings, causing them to sway back and forth. While any such movement may initially be minimal, high winds can create vortices that can match the frequency of the building they are moving around, causing noticeable swaying and shaking motions for those inside. This phenomenon led engineers to begin testing models of tall buildings in wind tunnels at design stage, assessing the potential impact of high winds on structures before they were constructed. By doing this, project teams were able to develop innovative approaches to managing wind loads, reducing their impact on tall buildings and enabling them to rise even higher.
If you stand here, you feel strong wind.
The first and by far simplest way to reduce the impact of high winds on a tall building is with an approach called corner softening. Corner softening sees sharp edges smoothed off of a structure.
Here is because now people provide some solution to reduce the wind load. Yeah, before, when people build tall buildings, they want to know the behavior of the tall buildings under the wind load. They will carry the wind tunnel experiment just to build small models, and in the wind tunnel that wind comes to test. They do the experiment, and then they summarize the principle. And they found
Make it more aerodynamic, or small cutouts created on the edges of the structure to scramble prevailing winds and reduce the strength of the vortices they create. A prominent
we change the section, the cross section, the building section. They can reduce the wind load. Remember, the corner softening in your structure design. When one day in the future, when you design the tall buildings, you can choose this method to change the corner. It can reduce the wind load. And there is a type A 101 of this building. They use this method to reduce the wind load.
example is the ornamental design of Taiwan's Taipei 101, where relatively minor cutouts on the building's corners reduced movement by as much as 25%. Tapering a building as it rises also breaks up the uniformity that causes vortex shedding. Kuala Lumpur's Petronas Towers and the Shard in London both use this technique to reduce the effect that high winds have on their structures. Taking things a step further, alternating a building's profile as it rises, and including setbacks, can also reduce the strength of vortices as they move around buildings. Some of New York City's early skyscrapers achieved this in response to the setback ordinances of 1916. But perhaps the most notable example today is the 828-metre Burj Khalifa in the United Arab Emirates, the world's tallest building at the time of filming. This remarkable structure uses a range of techniques to tame the wind and achieve its height, including an extreme taper, multiple setbacks, and a high degree of corner softening. We've demonstrated how the Burj Khalifa's carefully crafted design manages the wind in this simulation.
Here, I want to see before I see, we use the calculation, your computer calculation or hand calculation, right? Nowadays, for these buildings, it's really complicated if we just use hand calculation, is not to do this calculation, right? So we use the computer to do the calculation. Here, I recommend you software, the skill. Okay, if you have a free time, yeah, just to learn, then when you come, okay, you can here give you some tutors or some examples. They are all free, and you can try, yeah, to build some model or something in this platform, to do the calculation or just to develop a technique. If one day people ask you to do the wind calculation, you can use this software. Recommend you here. These skills. Yeah, if just you curious about wind calculation.
Developed using SimScales
This
software.
one, they do
With more than 150,000 users worldwide, SimScale is an easy-to-use, cloud-based engineering simulation platform that enables everyone to create powerful, high-fidelity simulations in a web browser. The platform can be tried for free through the community account, which gives access to thousands of public simulations to promote knowledge sharing and to crowdsource advice. Creating a twist in a building's form can also reduce the impact of vortex shedding. With every floor offset to the last, the number of bluff areas across these structures is considerably reduced, minimizing, or in some cases completely eliminating, the locations where vortices can form. Perhaps the most breathtaking example of this technique can be seen in China's megatall Shanghai Tower, which tames the wind and rises to become the world's second tallest building by elegantly twisting throughout its.
Yeah, look at this building I mentioned in the chapter 1, right? The appearance, they design like twist. That's good for wind to reduce wind load. Yeah, because use this method, wind comes. It causes tall building twist, but it's an anti-wind, anti-twist. Yeah, they have the good resistance. Yeah, in that. So if they use this method, also can, yeah, for us to construct high building in the design.
632-meter height. Another way to reduce the impact of high winds on tall buildings is to increase their porosity, cutting out parts of the structure and allowing air to flow through as well as around the building mass. This technique has been used in a number of high-profile skyscrapers around the world, including Saudi Arabia's Kingdom Center and the World Finance Center in Shanghai, China. But the most impressive example can be seen in New York City's 432 Park Avenue. With an incredible width-to-height ratio of 1:15, the tower is one of the world's most slender skyscrapers and the most prominent manifestation of New York's emerging super skinny residential tower trend to date. The 426-meter tower features double-floor cutouts at 12-story intervals throughout its height, allowing wind to pass through as well as around its extremely thin structure. We have again
They also use this software to do the analysis. They find for tall buildings, if you add some holes in the buildings, they let wind to pass through. It also can reduce the wind load. These things, just like us, civil engineer, they do the research, they do the experiment, they develop the theory, and the more things we realize, and the tall buildings we can build. Yeah, that's the meaning that we learn this course, this class. Yeah, okay, the class is over. Okay, thank you.